I hope that the line is clear.
Yeah, the line is clear. Yes.
Thank you. Good. So this is where this part we were looking at yesterday. We are trying to understand what is learning, following a fixed set of instructions, given an input plus the output, or give the input to a system, to a learning system, and let the system figure things out and learn as in understand the pattern and come up with the result. That's another way of looking at learning. So following instructions is just like identifying a human with one leg, two hands, one head, two hands, two legs kind of system. Whereas a proper learning is when you don't have to give these features, but it kind of figures out on its own given the picture of the human being. And again, we took the example of recommended systems yesterday. And I think this was the sheet that we were using. So we use an example of recommended systems where we try to understand what do these words mean. People like to also work similar to what we have matched. Um, that is basically what a recommended system is, which you will find in your Spotify, YouTube, um, uh, Netflix, any of these online streaming platforms. And we took the example of a person. Okay, so let's say this is the user profile. It has data about different individuals, and it probably has a database where it also has some sort of a ground truth. Uh, where given a movie, it has data about if there was this movie or not. Okay. Now, uh, uh, I know we made like a hard distinction as to we um kind of we said that okay, now we took the name of the movie and we decided if the algorithm will recommend that movie or not. But to just have in the back of your mind that that is an kind of an oversimplification, and this can also be like a genre of movie. It can also be an actor. It can be an artist. It can be a director. Like it can be anything that is related to the movie, right? The profile which we have here could be any of those, and that's what the system is trying to recommend. For simplicity, we took the name of the movie and we saw what's the best way to figure out the choice of this particular movie. And the first approach was to come up with some rule-based system, which was similar to the rule-based learning that we discussed. And then we introduced the concept of actual proper learning, where we took inspiration from the biological system and we looked at various aspects of learning. What really is a fundamental unit of the neurological system? And we figured out that it was a neuron. And we took an example of a neuron and we tried to see how the signal passes from one neuron to the other. And we also decided that the actual learning happens in this case called synapse when one neuron talks to another neuron. And in this context, we also talked about what's called the Hebbian postulate or the Hebbian hypothesis, Hebb's postulates, where we gave a statement that neurons which wire together fire together. So basically, uh, at a synapse, if learning is happening, that connection is strengthened, and if the signal from one neuron is not related to another neuron, if two neurons are firing randomly, then there is no learning happening in that synapse doesn't get stronger. Mm. And hence that connection becomes weaker. We took a similar analogy in the context of neural networks, and we assumed kind of that each input is going to be a feature, and the importance of that feature in predicting the output is going to be the weight that is associated with that particular feature. And then we have a bias term, which so basically the computational neuron is basically a dot product of the importance of feature one times the actual numbers in the feature one, importance of feature two versus the numbers in feature two, and so on. And the computational neuron basically is a summation of all these terms. And we also came up with what is called an activation function, which basically decides when that neuron should fire. And in a kind of a roundabout route, we also saw how this is very similar to a logistic regression. Okay, the audio is worse today. Is that what everybody feels?
It's clear from my end, Professor.
How about the others?
Yeah, it's good as well.
Okay, then Jeff, probably you should check your audio settings. Okay. Anyway, thank you for bringing it to my notice. Okay, now we kind of figured out that we have just reinvented the wheel. We came up with the same expression as for logistic regression. And we basically came to the same idea of logistic regression, but in a slightly roundabout manner, right? So this is basically an equation which a neural network would actually probably do in the backend. So this would be the constant. This would be the importance to this feature called weight. This would be the importance to this feature called loss product. And basically, we would come up with an equation, right? This is pretty much the same concept as logistic regression. But this is where the story gets interesting. From what we were discussing yesterday, let's move towards the subsequent topics and try and understand how did people fix this. Okay, that forms the bulk of today's session. Any questions from yesterday?
Sir, I'm not sure. I know somebody said they could hear you pretty clearly. I still find your sound is a little bit garbled. I'm listening closely to catch everything, but I just want to confirm. If not, I'll drop off and come back on again and see if it's me.
So, Lian, I'm finding it perfectly all right. You may please try to rejoin once and check. Maybe someone else also can confirm this.
Same to me. It's very
Yeah, it's loud and clear for me as well. I'm in Italy and it's loud and clear.
Okay, thanks, everyone.
It's not. I'm in Eastern Canada. It's not good for me either. I said it's a little to me. I'm struggling a little harder, a little more today than I was yesterday to kind of catch everything. But if you could just wait I guess maybe 10 seconds, and I'll leave and rejoin.
Sure, I can do
Professor.
that. Yeah, yeah, I can do that. Yeah.
All right. Thank you. I'm
So I think
gonna
it's the
leave
quality of
now.
the headphones. The mic on the headphone is causing the sound to sound like it's coming from very afar. I think it's a problem with the microphone that's attached to your headphones.
Uh, okay. So the microphone is basically a part of the headset. So
That's right. So if you can change
sure.
the input on Zoom to your default laptop input,
I'll try to do that. Yeah.
that would significantly increase the quality of the audio.
Oh no, it's actually um.
Okay, I'm back, Professor. Thank you.
Am I audible?
Yes, I can hear you now.
All right. So I tried to change and we couldn't take any other input. I think this is the only input I was trying to take. Okay. Anyway, if the problem persists, please let me know. I can try to main turn off the fan or something. Okay. So we had the sigmoid activation function. Just to give some context to in the world of activation functions, and we will actually look at this in more detail when we do the labs. Actually, these concepts become better when we actually try to build something. But for now, let's understand that there are different types of activation functions, and the most common is this sigmoid activation function, which we find right here. Okay. The activation function we can use for to solve linear problems, regression problems, is what's called a linear activation function, which you find right here. Some other activation functions are like the tan h function, hyperbolic tangent, tan h in short, and the shape of that is very similar to your sigmoid, but the sigmoid kind of goes from 0 to 1, whereas this goes from minus to 1. So it has more range and it's capable of giving better output, right? So, let's not worry too much about these activation functions. These activation functions basically are where this equation goes. So this is a function. Where am I going to put that function? Like the z term which you see here will be replaced by this whole thing. So at its heart, it's only the dot product currently. And how we use the dot product was what this particular perceptron does to the dot product is probably what the activation function really is about. Right? Now, what are the limits of perceptron? A perceptron is basically this, right? What are the limits of perceptron?
It cannot capture nonlinear relationships or
Yeah. So pretty much whatever we discussed as the limitation of the logistic regression, we are just carrying the ghost of logistic regression, right? So the limitation of perceptron is still there. Now, before these things became really popular, when the concept of perceptron came up, people were really excited and they were like, oh wow, this is the next new thing. Now it's going to It's going to change the way we automate things. This is the start of the brain. We can simulate the brain and all that. And then two guys uh, came up and told, okay, let's take a simple problem here. This is called the XOR problem. So this is called the XOR problem, where XOR problem. So basically, trying to say that if this is the input x1 comma y1. So this is my x1, this is my x2, and this is my y, right? So x1, y1 is 0, comma 0. The next point is 1, comma 0, which is here. The next point is 0, comma 1, and the next point is 1, comma 1. If this is my data point, and I want to create a model in order to predict, make a prediction for my y value, right? This is my y, this is my y dash, right? Basically, they stated the problem that, let's say there is one perceptron which takes input from x1 and x2, because these are the two features, right? So this is my feature 1, this is my feature 2. So feature 1, feature 2, a single neuron. Basically, we are doing a dot product. So x1, w1 plus x2, w2. It's a function of this. Now, this particular equation can probably predict. Okay, I come to that in a minute. And then we have another okay, so it's right here. So this will actually give a prediction, and this will give a line. Okay, give a line which separates out the data. Now, wherever we draw the line which separates, the data into two halves, not every data point is going to be accounted for, right? If I draw a line here, there's going to be one gray point and one black point, right? Like one from this category and one from this category. If you think of 0 and 1 as probably recommend or not recommend, right? Recommend and not recommend. That's what we are trying to solve it. Okay? So wherever I draw a line in this whole setup, that the separation of the data points is not going to be complete, right? There's always going to be, it's always going to be this or that, right? So I can either prioritize the 1, comma 0 data points, or I can prioritize the 0, comma 0 and the 1, comma 1 data points, right? So basically, the moment perceptrons became famous and they were trying to find their place in the world of AI, these two guys, I forgot the name, I can give you the name after the day. These two guys basically said that the perceptrons don't work, right? So the ad around the list of perceptron cleared, and people thought, oh right, yeah, I mean this has become an insolvable problem, right? If I'm going to account for the 1, comma 0 points, the 1, comma 1s are going to be excluded. If I'm going to account for these, then the other one is going to be excluded, because by definition, this equation can only produce a single line, and this data cannot be explained using a single line. So people went back and talked about how all this started, basically. And we went back and we thought, right, did we not want to recreate the brain? Wasn't that our original idea, right? Does the brain have only one neuron? Obviously not. The brain is made up of millions and billions of neurons, right? So people said, okay, so it's not surprising that a single perceptron is not able to deal with nonlinear data because that's not how the real world works. That's not how the real brain works, right? People don't have a single neuron in their head, they have multiple neurons. So that's when people thought, since many neurons are connected together, we will not make a single perceptron, right? We will make a perceptron which has multiple neurons. So instead of just sticking to one neuron where all my features come in, okay, so x2, this is putting a smaller zero, a smaller dot because this is the input neuron. Okay, so instead of saying, okay, this is what perceptron is going to be, they added one more quote unquote neuron here, one more computation neuron, and they said, I will send my input to both of these units. Okay, let this guy create a line, let this guy create a line. So I'm going to send in the same input to the second neuron as well. And the output will be a combination of these two. So now what has happened? This is creating a line, right? So the dark line is the one that is created from H1. This line is created from H2. And the output now is a combination of H1 and H2. And see now how perfectly this has explained the data that we have, right? So they said, yeah, it is correct that one single neuron cannot address the problem. So we will just put multiple neurons inside the perceptron, right? And they said, this is no more a neuron. We are going to call this a neural network. Okay? Is that clear?
Yes.
So from now on, it's going to be called a neural network. I'll just finish this, where there's going to be one input layer, one output layer, and this layer where we are going to put our neurons and we are going to let it do the computation. Okay, we are going to call it the hidden layer. This is my input layer, and this is my output layer. Okay, so the input goes into every neuron inside my neural network, and the output will be the combination of all these inputs, which is still the dot product. So whatever operation we did for this neuron, we're going to repeat for the other neuron as well. Yeah. What's the question?
Yeah, Professor. So the need for multi-layer perceptron is very well understood. But one question, if we go to the XR problem, the previous slide, if we keep the W1 as 1 and W2 as -1, then the sum at the Y point will become basically the difference between both. And now what would happen is the Y will match because 0, 0 difference is technically when I'm keeping the W1 as 1 and W2 as -1, what I'm trying to find is the Y will become the difference between them. And it will become 0, 1, -1, 0. Now all that what is required is the translation function or the trigger function need to be a function of type where at 0 it gives 0, but whether it is 1 or -1, it gives 1 as the output. So this way, just by changing the trigger function, we could have realized this with a single layer perceptron itself, right, Professor?
So you want to change the activation function and you want
Activation
to,
function.
yes, so you want to update the activation function,
So
still retain the rules of this perceptron.
yes, only thing is the weight W1 is 0, W1 is unity and W2
Yeah,
is
correct. So
negative.
you're saying whenever there's a negative number, make it a positive number.
Yes, the activation function, like we should, if only we had given the liberty to choose the activation function in a single layer perceptron,
Yeah, we have the liberty, yeah.
yeah, and then we could have very well done, like because we have such functions like where it is like a notch function, where at 0 alone it becomes 0, and below zero point 0.5 negative and above zero point 0.5 positive it becomes 1. We could have created a sigmoid equivalent function, and that
Correct. So you were making like a U function, right?
yes.
Yeah. Okay. That is, we want to just change the activation function and reduce the need for a multi-layer perceptron.
Yes.
Okay.
This was a question when I was reading the Ian Goodfellow's XR problem book.
Yeah.
It came to my mind. I know there must have been certainly a reason why the scientists didn't, go this way. If you come across any reasoning, please let me know, Professor.
Sure, I will try to find the answer, but I think from the top of my head,
yeah,
I think I would not be so. I mean, it might solve this particular problem, right?
Yes,
So,
yes, absolutely. I very much agree with you because there are two things required that just a single perceptron alone will not be able to solve the problem. Like we need a stack of perceptrons, and also like when we try to use the intermediate derived variables to calculate something else, and especially for nonlinearity, we would be requiring multiple layers. So we need stack of perceptrons as well as layers of perceptron. So I very much agree. Only thing is
the XOR problem.
Yeah.
That's what. So it might actually solve the XOR problem, but not explain the underlying the data. It might overfit for this particular XOR problem. If it's in the form of a bigger data, then maybe it will not work. That's the first explanation I can think of from the top of my head.
Sure.
But I'll try to think about it and I'll let you know, come up with probably a better answer. We can discuss this.
Sure, Professor. Sure. Thank you.
Thanks. Okay, so that is the origin of our first neural network with the hidden layer.
Yeah, Professor. Professor, when in a hidden layer, if the same data is being fired to all the neurons, right? So where is the strengthening of the synapses happening? Won't they all become equal in terms of a theoretical sense?
Correct. So our assumption is if one node, okay, I'm going to use the word node and neuron interchangeably from now on. Okay, neuron is two neuroscience. The more common term is what's called a node. Okay, so I'm going to just use the word node here, but it's the same as neuron conceptual. So the term, the node here is, okay, the assumption here is that this node will come up with one line. And since this doesn't know the weight that is getting assigned to the neuron number 1, H1. Okay, since H2 doesn't know W1, okay, I'll also put W3 here. I'll put W3 here and W4 here. Okay, so W3 does not know W1 and vice versa. W4 does not know W2. Okay, I think they are using different terminology, but I'll stick with W3, W4. The assumption is since it doesn't know what W1 is, the line that H1 is going to make is going to be different from the line that H2 is going to make. I mean, in theory, in a rare case, can they just repeat, can W2 just repeat, sorry, H2 just repeat what H1 is doing? Yes, it's possible. But the chance is so low that I think people kind of overlook it and say, okay, now no two neurons are going to come up with the same exact line with the same exact story.
Got it. This is helpful. And just another follow-up. I'm presuming that the threshold or the bias is not there because it has to be trained, this model, with whatever data.
Yeah, correct. So,
Yeah, okay.
so from now on, the bias term is always going to be there in all our discussions, but we are going to put it in the back because people usually, because it is usually like adding a constant or something. Okay.
Okay.
So we are not going to majorly discuss it. We are going to be concerned more about the weight, but the bias term is there that gets added. So it's there in the mix. Okay, so conceptually, this is what is happening. But in terms of the feature space, what's happening here is now each is a transformation into a new feature space. So this is almost like you have two data and then you have PCA, you do PCA, and then you build your model. Now the PCA is a new space, right? Except you are actually creating that feature space manually. But in neural network, that feature space gets created internally. You just feed the data into the neural network, and whatever transformation it wants to do, if it wants to do, instead of x, if it wants to do x squared, right? If it wants to take log, if it wants to do a square root, right? So all those feature transformation, the neural network is doing on its own. Okay, so the input that we are going to give gets transformed into a new feature space. Some sort of a new transformation matrix is created, and essentially the matrix, that new feature is used to make the prediction, to make the y naught here, to make the y naught, y hat, right? That is one of the major takeaways in a neural network, right? The hidden layer acts as a feature engineering space where we don't any longer create those features, we don't engineer those features, but those features are automatically created. Right? Any questions still here?
What is new space?
Was that?
What is a new space? You see, each
Feature
domain
space.
responds.
Into a new
What is
feature
a
space.
what is a feature space?
Okay. So the feature space is basically we are trying to do an x1 comma y1, right? When we look at the data with two features, x1 and y1, we are trying to do x1, x2, and we are plotting all our data points here in this space, right? So after each pass, after each hidden layer, instead of plotting this data in an x1 comma x2 kind of a feature space, after every layer, it gets passed on to, as you can see here, the h1 comma h2 space. right? So it is creating its own variables, its own understanding, its own representation of our input features, and it is trying to use those as values in order to do the y hat prediction.
So the new space is like another plane, is it? A different
Yeah,
plane.
yeah, correct. With different numbers, yeah.
Mm.
Instead of doing x1 comma x2,
Yeah.
right? It's now working in the h1 comma h2. Why? Because this is h1 and this is h2, or under the other way.
So H1 and H2 are different planes. They are different from X1 and X2. They represent a new
Correct,
plane.
correct.
Okay.
A completely new plane, a completely new set of numbers.
Right.
Okay, and it manufactured it on its own. That is the thing. We are assuming that, let's say, if x squared is what we want to convert x values to x squared, let's see, if x squared is predicting the y hat value better, or a logarithmic scale is going to predict the y hat better, we we actually did the log conversion. We are assuming that it is just figuring it out on its own, and it is doing a VCA, or it's doing an log or x squared or the root x or whatever.
So no human intervention.
Yeah,
The layer it will create its own hidden space. H1,
correct.
H2, H3, H4, H5, H6. No
Correct.
human intervention.
Yes, correct. That is correct.
Oh, oh, okay. Thank you.
Okay.
So just one more
Now
question.
this is
In terms of the hidden layer, are there multiple hidden layers that get created, or is it, how do you, like, can you explain a little
yeah.
bit in terms of, I mean, is there a
So
technical complexity, or, it does get more complex?
it does way more complex. It gets way more complex, but that is for the next sessions.
Okay,
Right now, we will understand how even this is so complex,
okay, got it.
right? So we'll discuss how even this simple architecture is way more complex than what we would expect.
Okay, got it. Thank you.
Okay, right. So now you remember in the first class, I talked about the iris data set, and I told, okay, a single line is probably never going to be enough to explain the whole data set. Okay, it requires two lines, right? And what we have here is basically, this is my logistic regression. This is my neural network. Now, using this very simple same architecture, I can actually create two lines. I can create the first line that goes like this, and I can create a second line that goes kind of like this. And now I end up with something that goes like this and then bends, right? Forgive my line drawing skills, but I'm just saying that the two lines got combined into some weird shape, and this transformation kind of happened inside the feature space, and it was the output neuron here, the output neuron, which probably combined these two lines into this weird line with a bend, right? So even such a simple architecture, we are ready to see that it is, it can solve some of the problems which our basic logistic regression was not able to solve. Okay. Okay, and that's basically what uh, what a neural network is, right? We can have as many neurons as we want inside the hidden layer. We can have as many inputs as we want. Okay, we can have as many inputs as we want. If we go back to the recommended systems, remember this was my age. This was I don't know, language, right? Other features. Now remember where it got really out of hand is when the data got more and more complex and we didn't know how to really extract features from a particular column, right? So let's say I have this number of clicks on an icon, number of clicks on a genre, let us say, on a genre of movie. And let us say this is, when we scroll, actually Netflix probably also corrects the time that we pause for an icon. Okay, so the pause time over an icon or over a genre of movie.
I have a question.
1 minute, just 1 minute.
Sure.
Over a genre of movie. Okay. Now this is my first feature. This is my second feature. This is my third feature. This is my fourth feature. Right. Now let us say that feature 3 and feature 4 are redundant. Okay, they give the same information, but I'm not sure, right? In traditional ML, what would I do? I would try to find a correlation between these two, and then I would probably try to do something which reduces the correlation, and then get rid of these two features, add the third feature, and then try to build a model and all that, right? In the case of neural network, I'm just going to dump all the four features into my neural network. I would assume that somewhere within the hidden layer, there is one node or one neuron sitting, which is automatically going to figure out that feature 3 and 4 are correlated. So I'm going to create a hidden space which addresses that correlation and use that feature to make my prediction. Right? That is basically what we have in our neural. All right, go on.
So, what is the importance of identifying this middle layer as a hidden layer versus a second layer or a third layer?
Yeah, that's just a fancy term. Okay. We can very well call it the Excel layer or the first layer. Now we are talking about you're going back in time, and right now we know that we can add multiple layers. Right? But during the time when these things came out, people had only one layer to work with, right? So there was an input layer and then the output layer. And the middle layer, you can just call it, I don't know, computation layer or middle layer. They just gave a fancy name to it and called it hidden layer. That's all. And there's a reason why we call it a hidden layer also, because we don't know what combination is happening inside. And we are just assuming that it is doing some PCA, it is doing some x squared, root x, log x, some transformation it is doing. But there is no way to find out what it is doing inside actually. Okay, so its computations are hidden, and hence the name hidden layer.
Got it. Thank you.
So so that's basically the founding architecture. Okay. Now for this to be successful, remember every input feature should go to every neuron in the hidden layer. Okay. Input feature 2 should go to all the neurons. 3 should also, and 4 should also. This is very, very important. Why? Because each neuron in the hidden layer should see the raw data. That's how each of it will do its own thing and come up with one way to explain the data, explain the pattern in the data, right? Um, in a way that that's what makes it efficient. It may be counterintuitive and think, okay, what if the two neurons are doing the same job? That's a real risk. We will come to that. But depending on the volume of data, or depending on the complexity of the data, we can have more neurons in the hidden layer or lesser neurons in the hidden layer. But all the neurons should see every feature from the input layer, right? And the output should be a combination of all the manufactured features. Okay, so both of this is going to be very important. The input should go to all the all the neurons in the hidden layer. The output should come from all the neurons in the hidden layer. Okay, and building it. Okay.
So here, the output, is it like a predetermined output, or it can be an output that can change based on the computation by the hidden layer?
Yeah, so the output is going to change depending on the computation, and I'll come to how the training happens, how the testing happens, and all that.
Okay. Thank you.
Excuse
And
me. So for the hidden layer, from what I understand is that it can be layers, right? Because it can be computed for many times or trying figuring out, and it can be layers or layer, right? So it you just combine into one hidden layer, but and then the second thing is and so it can automatically get rid of not necessary data within that layer, and then come up with the output layer. And yeah, that's what I understand. If I wonder if that's is correct.
very much actually. So that's one of the things with the neural network, right? So we can actually dump all the data that we have, and if a feature is not important, consistently all the nodes will say that it's not important. It will not use it for the model prediction. So it kind of gets thrown out. Yes.
Yes, and so that I guess there will be some way that we can maybe this hidden layer also test test the expected output too, and then it's gonna test like the percentage of maybe correctness, and then give us the highest correct output.
Exactly.
Yeah,
That's
and
exactly
then
what's going to happen during the training. Go ahead.
and the last question would be, you said that the neurons should see the features. Could you please explain quickly on like how it see it?
So when I say C, I'm just saying that all the input features should be fed into all the nodes in the hidden layer. That's what I mean by C.
Got it. Thank you. Thank you. And then the human, as human, we will to test the output by there will be some method or way later that we can test the output of that. Thank you.
Yes, very much. Yes. Yeah, Deepak, we had a question.
So just a question on the hidden layer and the weights assigned for each of the neurons, right? You said like we can't be sure that the neurons will be doing the same thing, different neurons doing the same thing. Is there a conscious thing of changing the weights on each of the neurons, which makes it like getting different outputs and using that to kind of test it rather than it's just by chance that neurons are going to do different things. Like, how is it that we are sure that the neurons will do different things and the multiplier thing works?
Yeah. So how do we know that it works? Because we are going to start with, when the training comes, we are going to assign random numbers as weights. Okay, because we have absolutely no way of finding the weight, right? So we are going to assign different values as weights. Okay. So when the input weights are random, the random number that is generated for this neuron is going to be different from the random number that is generated for this neuron. Right? So that's one way of that. That's how we start ensuring that no two neurons do the same job.
So we assign the weights randomly differently for each of these neurons.
Yes, that's what happens during training. Just give me 1 minute, I'll get there.
Sure. Sounds good.
Okay, so now I hope we've had our discussions, and how I hope that you are convinced that with this neural network, or generally neural networks, are capable of solving the nonlinearity problems. Okay, so we can give data that has a very weird shape, and hopefully it will be able to pick up some pattern, by different combinations of different input numbers. We are hoping that it will come up with a very complicated, sigma I squared integral differential whatever equation. It is going to create this shape on its own and explain the data to us. Okay, use it for model prediction.
Professor, one question.
Yeah.
So when we were studying the linear regression in machine learning, we understood that to support the nonlinear functions, we have to manually plug in the transformative functions, right? And here, what we are doing is technically like we are allocating few layers for that purpose, and we expect it to be automatically done by the neural network as part of the learning process, right?
Exactly, correct. That is the primary difference between machine learning and neural network.
So technically, we are offloading the feature selection, feature engineering, as well as the transformation to the automated learning.
Correct.
Thanks.
We are automating that process. Exactly.
Yes.
Okay. We'll come to the advantages, disadvantages of that approach generally, but based on what we have done till now, what could be the advantages and disadvantages of neural networks, of generally offloading the feature engineering task, automating it? Pros and cons. Yeah.
Yeah, one follow-up question, Professor. So, can we say that the feature engineering is not that important when it comes to neural network because it takes care of it, or we can achieve better mileage if we do a certain level of feature engineering manually, if possible?
You see, people have tested that, and it the answer depends on how much computational power you have, right? So if you are going to make the job of neural network little bit easy, right, and you have very limited compute, then yeah, maybe it will make a difference. But if computation is not a problem, right, then we just add more neurons, more layers, and let it handle the feature by itself.
Thanks, Professor.
Okay. Anybody wants to?
One question. Sorry, Professor. So when Niyas was saying that both the feature selection and feature engineering will be taken care by the neural network. My understanding was it's only the feature engineering part. The feature selection has to still come from the user.
Like feature selection, we just dump everything at the neural network.
Oh, okay.
Whatever we have, if it's not required, it's not required. Like I said here, if the number of clicks on a genre and the pause time over an icon, particularly if these two are not important, it's just going to throw it away. Or if it's going to say that, okay, both of these variables is going to give me only one information, it will extract that. It will combine it to give the third feature.
Got it. Thank you.
Okay. I used to use this example where if I give them miles per gallon, weight, horsepower, the cylinder, will can a neural network predict if this car will be a manual or an automated? That is the AM. Is it manual transmission or automated transmission? But I think I'll have kind of moved away from that example and moved more towards recommended systems. Uh, because I've been doing this over 6, 7 years, and Netflix got really popular after COVID. So I'll just quickly, with the same background, I will give the example of the Netflix example that we have been talking about. So instead of weight, we are just going to have the user profile. Okay. Instead of this thing, we are going to have the language. Here we are going to have the nationality. Okay. And based on this, it's going to make a prediction as to will the person like movies belonging to a particular language or not, let us say. Okay. Language, Hindi or not. Hindi. Okay. If that's what it's going to make, there are a couple of terms that we need to familiarize ourselves with. Firstly, the parameters. Okay, the parameters are some things that are that basically help me with giving the correct output. Okay, and things which I cannot really control. Okay, these things are learned during the training process. So in this example, parameters are going to be the weights and the bias terms that is going to be associated with each of us, right? But in terms of neural network, we have this term called hyperparameters. Okay, so a hyperparameter is something that I can control in order to make my neural network better. Like for example, I can control the number of neurons that go into the hidden layer, right? I can control what function is going to be sigmoid or tangents or what the activation function that I'm going to use for every hidden layer, for every neuron in the hidden layer. I can control, people usually don't do that, but I can control how many inputs I can give to the neural network, right? I can control the cost function. What do I mean by cost function? Let us say I have a y and I have a y hat. Okay. How am I going to calculate the error? Y minus y hat is usually the way, but we all know the problem with using y minus y hat. If I have one error which is -4, another line that gives 4 error, then 4 and 4 is going to get cancelled and I'm going to get an error 0, which is not representative of the actual data. So I either take a modulus or I take a square, right? So I have a sum of square error or I have mean square error. So what is the cost function that I am going to use in order to reduce my error terms? That is something that I can control. That is a hyperparameter, right? So these things are due to the neural network, right? Especially the number of layers, the number of hidden layers, the activation function, and the cost function that I'm going to take to do my error calculation, right? And what is the correct number for these hyperparameters? We'll never know. That is something that we have to only adjust and tune and change the number and see how the errors are. I mean, add or reduce the number of hidden layers of the neurons. These things, the parameters which I can control, they are called hyperparameters. Is that clear? Any queries?
So can you explain once again, if that's okay?
Yeah, sure. So I'm talking about this concept called hyperparameter, where in a neural net, where this is probably a new term and a new concept. Okay. So when see where I'm introducing the training. So here where I talk about training, but I'll talk about it more. I'm going to open the whiteboard. Okay. So how does at least up until this point, how does a neural network learn? I have my input parameters, and then I have my neurons in my hidden layer, and finally my output layer. So this is a neural network that takes 5 input features. It has one hidden layer, with 4 nodes or neurons. That's the architecture of this neural network. Okay. Now, what really is training in terms of neural network? What I mean by training is the first row of data comes. In our case, we are using the recommender system, right? So user profile 1 with the features age, with the feature the sex or their gender. And third would be what did we discuss? Language, right? Nationality. What else did we use? Nationality, language. Give me something that is
Income.
income. Very good. So income. Okay. So I'm trying to predict using all these features. Okay. So user 1 has all these, and I'm trying to see if they will like a movie from the action genre. Okay. So can I recommend action or not action? This is the recommendation that I'm trying to make. Right. So there is always a correct answer for this, or I will not, to make things easier, just I'm going to make a small change. Pardon me. So instead of getting the action score, things are always easy when the problem is a regression problem. So I'm going to give a score for this person. Okay. The score basically is how much will this person like an action movie? So maybe it tries to score me from 0 to 10 or something, probably 0 to 100. Okay. It tries to give me a score from 0 to 100 for my action preference, action movie preference. Okay. And let's say that internally it has an algorithm where each profile has, it has, based on a lot of things, it has calculated and a preference score for a particular genre. So this user one has something, the user two has another score, user three has another score. Okay. That is my Y value, which I'm trying to predict here. Right? Now, okay. Now here is my output neuron. What happens really in training is the input goes to all the features of colors. Okay. So, okay. And let's assume that the same input goes to the other neuron also. Okay. And it is giving me a score, which is basically my y hat, and it is trying to predict the score for every user. Okay, so user 1, what is the y? User 2, what is the y hat? User 3, what is the y hat? That's what the neural network is doing during training, right? Now, how does it really know um, how to how to do the training? Remember, it is all weights here, right? So feature 1, W1 times H1 or W times 1 times, what did we call this? Let's just call it F1, W1 F1. W2, F2, W3, F3, and so on. Okay. How does it decide the W1? Initially, the neural network just tries to assign random numbers as weights. Okay. So, and it is actually absolutely random number. So W1 could be root 2, W2 could be 0.56, W3 could be 5.32, and it tries to make a prediction. Right? It comes up with the y hat, compares it with my actual y score, takes the difference, and depending on what error function, what cost function I'm trying to do, it can do a sum of square error or mean square error, or it can take just a modulus, the absolute error, right? And that is exactly how it is deciding the phase during training. Okay, this is the final output. Okay. So when I say a neural network is getting trained, it is basically the weights which is getting the numbers which are assigned to the weights that I'm talking to. Which combination of the weight will give me the smallest error in my output is what I'm trying to understand when I train a neural network, right? So which combination of W1, W2, W3, and hence here also the weight in oh, sorry, this should be 22. it's a 21 or 22. So the weight of this hidden layer, the weight of this hidden layer, the weight here, the weight here. Okay, so that's basically what I'm trying to adjust, or what the neural network is trying to optimize when it is trying to learn or predict the values in my output. Okay, that is learning in terms of neural network.
May I have a quick questions regarding the score you give it for the
Sure.
output? Um, so is that like it's automatically score a score based on what does it mean by you give it a score?
So I gave it, so internally, the score is what I'm trying to predict. Okay. It could be because we are talking about recommender systems, right? So it's a score for how much I'm likely to prefer a genre of movie. Okay, just a hypothetical situation.
Mm-hmm. Got it. And then it's gonna and then regarding the wage for each parameters, first we're gonna put in input from our like own point of view in that okay, so this will wage more than other parameters. Will the hidden layer be smart enough to figure out if we have any bias in it according to their own calculation?
Yeah. So ideally, the hidden layer should figure out the correct way, but we are not quite there yet. Okay. We are going to hit another technical snag, which is going to put AI in the winter for maybe 10 years. Okay. I'll come to that in a minute.
Thank you.
Yeah, Badr and Bruce.
Yeah.
I have a quick question. Go ahead, Badr, go ahead.
Go ahead, Nimish, no problem. It's okay.
Yeah, I'm sorry. I mean, it might feel like a stupid question here, but
No
I just
question
could
for
not.
sure.
I just could not get my head wrapped around like why should we do why should we use neural network if let's say because ultimately we have a data set and we are trying to get an output from the data set. So if let's say I have a data set which is like 1,000 line items, 1,000 rows, right? Will it be worthwhile to allow the neural network to do their own feature engineering, or would it be beneficial for us to do a feature engineering and get an output from that
Point
data
of
set?
a neural. Okay, so the point of a neural network is basically going to turn off the video. Sure.
Yeah, sorry.
So the point of a neural network is basically when the data really gets out of hand, like when we have is it the features that we try to.
Doctor, your voice is breaking.
Yeah, no, I'm not speaking. I'm just trying to. I'm trying to change the screen to my back
Okay,
to my
I thought you were.
slides.
Okay.
Go to one seconds.
Nimesh, can you mute yourself?
Yeah, we hear some noise, I think, right?
Yeah, I think it's from the animation symbol. Sure. Even I can hear that. Okay, so the point of using a neural network, remember, now we have age, gender, location, all these data, and also some things that we cannot directly do any feature engineering on. We don't even know if it's important. Okay, movies that were rewatched, or genre of movies that were rewatched. Okay, number of clicks on rewatch, what is the login device, what is the time of the day, number of minutes that. So now we have collected so much data that we know it might be useful, but we don't know in what way it will be useful, right? So now manual feature engineering becomes extremely hard because we don't even know if this data makes sense. We have a hunch that somewhere in the mix this number could be useful, but we don't know how useful this number is going to be. That's where we dump this data into the neural network and say, okay, you figure it out. If it's important, take it. If it's not important, like you also generate new features from it and use it in any intelligent way that you see fit. That is the first point of a neural network, right? Secondly, if there are more missing values in the call, if I have so many features, complicated features, difficult to extract features, then at some point manual feature engineering becomes really tedious, right? That's another place where we want to use the neural network.
Okay, got it. Thanks, Professor. Yeah.
Great. Now, Badra and Chris.
Yeah. My question is, does the hidden layers give us the indication that the system performance is good or bad? The more hidden layers we have, tell us the system's performance will be good or bad or something like that.
See, correct. So that is very intuitive thing, right? So if the idea is I want to extract as many features as possible, then let me just add more and more hidden layers, right? Intuitively, that's a very, very correct approach, actually. And people have tried that. Um, when we do deep learning, I think this answer will be answered. This question will be answered. Okay. What is the problem with that and why it is actually intuitively correct? Theoretically, it is correct. Okay.
But I
But
think
what
it's gonna
problem
come with
happens?
cost. Gonna come with cost, maybe.
It's going to come very close to the correct answer. Correct. Yes. Yeah, Prince.
Thank you.
My question is very much similar that what Bala has asked. So, in case if I'm having if I select an activation function like sigmoid, right? And if I keep the hidden layer, one or two hidden layers, not more than that, for the efficient way, if I increase the hidden layer, then I will get better results. Or if I choose an activation function which is very efficient and can give me better results. So what which option will get a more weight? Choosing a right activation function or increasing the hidden layer?
The answer is both.
Then
Okay.
how will we
Yeah,
decide
how?
that?
How is again part two next session when we do deep learning.
Okay, perfect.
DNN. Okay.
So it means that increasing a hidden layer, as a single option will not give me the accurate results. It means I need to tweak in such a way so that both aligned properly and allow me to get a expected results.
Correct. That would be the correct approach.
Okay, perfect.
Okay. So this architecture, which we discussed just now, is what is called an artificial neural network. In other words, it is also called a multi-layer perceptron. A single layer perceptron was basically this. Sorry, this is my input. This is my hidden layer. This is my output. This was my single layer perceptron. This whole unit is going to be called a perceptron. Okay. When I add one more layer, it just becomes a multi-layer perceptron. Just one or two layer. And you can actually call this a multi-layer perceptron. Like even without this, because this includes an input layer, a hidden layer, and an output layer. So the name that is going to get is a multi-layer perceptron. In other words, you can also call it a feed-forward network. Why? Because the information is always going in one direction. Okay? The information is always going in one direction. I give my inputs, some computation is happening here, and I get an output. And then I get a error score. Okay, so this architecture is what's called a feed-forward architecture, or in other words, you can also call it a fully connected network. Why? Because every neuron, every node is connected to every other node in the subsequent layer, in the upcoming layer, right? So this is connected to all three. This is connected to all three. This is connected to all the three in other hidden layer, and the output is connected to all the three neurons in my hidden layer, right? So in that sense, everything is connected to everything else, and hence it is going to be called a fully connected network. Okay? All these three terms, they more or less mean the same. A fully connected network, a multi-layer perceptron, a feed-forward network. The umbrella term is artificial neural network. Why artificial? Because we are assuming that in a natural neural network, this is going to be a physical neuron, and all these are physical neurons, and that's actually how neurons communicate with each other, right? So there is one neuron always talks to multiple other neurons. It gets inputs from multiple neurons. So that is a natural neural network. This is a artificial neural network where we took inspiration from the biological neuron and we simulated the computation. Okay. Any questions still here? Is it time for a break now? Can we come back in 12 minutes?
One extra question, Professor.
Sure.
Yeah, before the break. Yeah, may I know the physical neuron actually?
It what?
May I know the physical neuron is doing backward and
Please.
forward propagation actually in biological way.
Okay.
Now we just
So,
study the forward one, right?
so a physical neuron, I mean, that goes too much into neuroscience, but a physical neuron doesn't really go back and forth, but there are mechanisms within the neural system where there is always a feedback mechanism as much as there is a feed forward mechanism. So there is a feed forward network in the biological way. There's also a feedback way where some signals actually travel in the reverse direction and they feed to the system which actually feeds it.
Got it. Thank you very much.
Right, thank you. So let's come back in 12 minutes. in its beginning. Now, we saw how neural networks basically train. We just deep dive into that and try and understand what is it in the neural networks that actually can be considered the training process. Before we get there, just to wrap up our understanding of multi-layer perceptron, a neural network, the kind of neural network that we have talked about till now, and ANN, multi-layer perceptron, or a feed-forward network. It's a network that is made up of multiple neurons or multiple nodes, where each of these neurons we are going to call each of its neuron, each of the neuron, computational neuron, is going to have its own activation function, like a sigmoid, or there's the word ReLU, but we'll come to that in a minute. Don't worry about it for now. So a multi-layer perceptron is what we talked about. It. So the whole unit is called a multi-layer perceptron. An artificial neural network, which we just built now, is characterized by what are called parameters and hyperparameters. The parameters are fixed. It's fixed upon the number of input features, the number of neurons in a hidden layer. Okay, the number of neurons in a hidden layer, and bias terms. Bias is what each neuron is going to add to the computation. So it's usually a constant which scales up or scales down the response of the neuron, right? And by learning or training, what we mean is what correct combination of weight will actually predict the correct value of y. That's what we mean by training a neural network. Okay, or by what we mean by the weight of the parameter. The weight parameter, right, is basically the one that determines how well a neural network has actually learned the data. Now, apart from parameters, there's a term called hyperparameters. Hyperparameters depends on the number of neurons, the number of hyperparameters is something that we can control. Parameter is something that is usually fixed, right? Once we send in the number of, once we send in all our input features into the neural network, those are the parameters that you can calculate the number of parameters, the weights and bias within an artificial neural network. But hyperparameter is something that you can control and you can optimize, right? So that can be the activation function, that can be the cost function, that can be the number of neurons in the hidden layer, or the number of hidden layers itself. Hyperparameter is basically something that determines the overall structure of the neural network. For now, let's understand that for a regression problem, a linear activation function is used, and for classification problems, the sigmoid activation function can be used. Okay. Finally, we have the output layer. The output layer is is basically again an activation function which is present in the output layer. So the nature of activation function that we use in the output layer and the nature of function that we use in the other layers within the neural network can be slightly different. In our hidden in the hidden layers, the activation function is usually sigmoid. Okay, Whereas in my output layer, depending on what problem I'm trying to solve, it can either only be a linear activation function. It can be a linear activation function, or if you are trying to solve a classification problem, it can be a sigmoid activation function. Okay, the sigmoid activation function, or a tangent, which we have discussed in one of the previous slides. We'll talk more about this when we probably do the lab or in DNNs. This is going to keep coming up. Okay? That is the difference in the activation function between the hidden layer and the output layer. In hidden layer, it's usually the sigmoid function, or sometimes even what is called a ReLU activation function. Whereas in the output layer, depending on what problem you are trying to solve, it can either be a linear activation function or it can be a sigmoid or tangent activation function. If we are doing a multi-class problem, we can either have multiple output neurons, but that's usually not what is done. We use what is called an softmax activation. Okay, so again, we will when we do the lab, we will understand because when we actually see the result, it's more it's easier to understand the what the softmax activation function really is. Okay, but for now, if there are three possible answers, okay, if there are three possible answers, which is typical of multi-class problem, more than two, okay, let us say there are three answers. The softmax basically gives a probability score for each of this, right? So for a 0 or 1 or 2 classification, the softmax is basically going to say there is a 0.9 probability that this is option 0. There is a 0.02 probability that this is 1 and a 0.08 probability that it is 2. So if you add everything, it comes to 1, right? So that's basically what a softmax activation function is. This is more or less fixed. So if it is a multi-class problem, use softmax. If it is a classification problem, use sigmoid or tangents. If it's a linear problem, if it's a regression problem, use a linear activation. Kind of fixed. And similarly, in a hidden layer, the activation function that we use is usually a sigmoid or a ReLU activation. Why? Because it works best. And when we do further classes, when we do DNNs, we'll understand why people don't break their head over these things and just go with some of the preset activation functions. Okay. Any queries will give?
When would we use the tanh activation function, Professor?
Okay. So the tan h is basically a function which goes from -1 to 1. So the sigmoid, I think I had it somewhere in my previous slides. Okay, so here it is. So the sigmoid basically goes from 0 to 1, whereas the tan h goes from -1 to 1. When you use it, when we have, and when we do DNN, we'll understand. There's an exponent term sitting here which can make really crazy things to a neural network. Okay, and the tan h kind of solves that problem. Okay, when we want negative values, you see what happens in tan h is for a -1, it actually gives a -1 value. Whereas this is more like for a -1, it gives a very high positive value, right? So the scale is kind of not consistent, not linear. So when we have more, when we want to deal with negative numbers and such, the tangent just gives us more range to operate with, -1 to 1.
Sure, thank you.
So, Professor, in case of the softmax that you explained, where probability is being used, right? So, won't the least error be the outcome? Why do you need to use probability?
Okay. What do you mean by that? I don't understand your question.
So, when at an output level, right? So, my understanding is that you have there is a possibility of three outcomes, correct? Three outcomes, right? And you may want to choose one outcome at the end of it.
Correct.
Right? So when the outcome is being determined, okay, the statistical error, wherever is the lowest for these outcomes, won't that be a natural choice in terms of the decision?
Oh no. So this is for an unseen data. We want to make a prediction for an unseen data. Okay, let us say that I want to classify a user into will they choose action or drama or comedy, one of these three. Okay, so given a user profile, what is the most likely genre that this person will choose? Is what I'm trying to make. Right. So when the training is happening, it kind of groups the whole data into these three groups, right? Because I mean, if there's a clear distinction based on user profile, that's how the data should be. There should be one group here, one group here, one group, in three different places, three clusters kind of a thing. And hopefully it will come up with a different approach for each of this. So what it does is at the end of the training, it has a way to give a probability score for each of these three genres, each of the three possibilities.
Got it. Got it. So will there be another?
It is not choosing anything. It is not choosing anything.
Got
We
it.
are choosing the one with the maximum probability. It just gives us the probability score.
Thank you, sir.
Go ahead. You had a follow up. I think I cut it short. Sorry.
No, I'm good, sir. Thank you.
Yes. Now, how do we train? Coming to the main part of the neural network. Let's say this is my input data. Okay. Given an input, this is ultimately what I want answered from the neural network. Let's say I'm using this cost function. This is my prediction. This is the actual ground truth, and I'm using sum of square error in order to make my in order to calculate my cost function. Okay. So how does it work in real life? Okay. So that is my first data point, user 1, user 2, user 3, and then I have feature 1, feature 2, feature 3, feature 4, etc. And I want to make a prediction as to will I choose action movie or not choose action movie. Okay. Let's say that is the prediction that I want to make. Okay. So how does it really create this? So how does it really do this? We told that we are not going to do a classification because that's just messy for teaching. Let's convert it into a regression problem, and I'm going to give a action score. Okay, I'm going to come up with an action score for each user, and I'm going to give an make a suggestion based on the action score. If the action score is more than probably 0.5, 0.4 something, then I will suggest action models for this user. Okay, that is my idea on which I am working. Okay, now based on all these features, okay, there is a actual Y. Okay, and during training, the network calculates the Y hat. Okay, the Y minus the Y hat is going to be the error. Right? Our point is to minimize this particular error that I am getting. Correct? And in order to do this, I am using a neural network where I am going to assign a weight term for each of these features. There's a weight 1, there's a weight 2, weight 3, etc. And I'm going to create a neural network like that. Okay? And I have an output. The output is a linear activation function. All these are sigmoid activation functions. Okay. So during training, now I'm starting the training, right? I am giving my input value, whatever for user one, whatever number is there here, I'm giving that. And I am starting with a random weight. Okay, that is my initialization process. Okay. While I'm initiating the training, I am randomly allocating numbers for all these weight terms, W1, W2, W3. Okay. Till now, I've already explained. I'm just repeating what I've said till now. Okay. I've also decided the cost function. It's going to be y minus y at whole square. Okay. So for user one, I'm getting an error. For user two, I'm getting an error user three, and I'm adding everything. And that is the sigma term here. Sigma y minus y at the whole square by sum of errors square. Let us say that I'm getting a huge error term, 21,568. Okay, this is my error term. Okay, and the action score basically ranges from 0 to 100. We all know that the error term is useless without knowing the range of the score here, correct? Because if the range is between 0 and probably 1 million, then probably 21,568 is a decent number. It's still big, but it's not something that I'm going to worry too much about. If this number is 0 to probably 10 million or something, or 1 billion, right? But if the score itself is 0 to range is 0 to 100 and my error score is 21,568, then definitely something is not right with my training, right? Now, how will I change the weight? How will I minimize the weight? How will I change the weight such that this error term is 0 or is close to 0, because that's what we want through our training, right? The error, the cost function should be 0 or close to 0. That's what we are aiming for. Okay. The way that I designed this is I randomly gave numbers to W1, W2, W3, W4, etc. up to Wn. I gave random numbers for this, right? And that gave me a score of 21,568, which I think is a huge number. Now, how will I reduce this number? That is the heart of the problem that we are trying to solve, which is training the neural network. How are we going to train the neural network? The goal is to reduce the cost function, bring it down to a number that's close to 0. Till here, any queries? Any questions? So our task is to minimize the E by updating the W. The query is how can we do this? Remember, at this point, we are only doing feed forward. Okay. So what people actually did was, one of the things that we can actually do was, uh, in order to solve this problem, by still keeping it a feed forward network is initiate W1, W2, W3 random weight numbers and calculate the error, right? And then initiate different set of random numbers, forward propagation, calculate errors. A different set of random numbers, do the same process. Okay, do this probably 100, 200, 300, how many ever times that it requires. And then choose, freeze the weight, which gives us the minimum error. What do you think of this approach?
Is it a feedback?
It takes a lot of time. It's long.
Not efficient enough. Not so efficient, I think.
It's not efficient, right? So, okay, Olga, yeah, go ahead. What's your question?
Okay, now forgive me. Oh, wait a minute. Yeah, forgive me if this sounds kind of strange. Um,
Go ahead.
but how are we? This I'm trying to formulate the question. Okay, so you have all the different, all features are all weighted randomly. Would it be that each neuron would be calculating its own error? So you're feeding all the data into each
Correct.
neuron,
Yeah,
and each
correct.
neuron will be calculating its own error range like this.
Now,
And
exactly.
then
So,
those results are being fed to the output.
see, that's the ideal situation we want, right? We want every neuron to have its own error term and kind of work on its own, right? But where are we calculating the error? The only place we are calculating the error is the output, right? Because by definition, these are hidden layers. We do not know what's happening there. So there is no correct answer in the hidden layer to compare a neuron's output with, right? So calculating the error term at the level of the hidden layer is by design not possible in a neural network. Why? Because there is no correct answer there. The only place where we have correct answer is the output. So that's where we calculate the error. Does that answer your question?
No, I just made it worse, but okay.
No, I mean let's address it. What is it?
Um, I think I probably missed something in a previous class or something, but um, the whole notion of training. If I have no idea, if I can't compare the nodes between each other, then like okay, let's go from one layer to the next, right? Two layers, okay. I don't have separate features anymore when I go from one layer to the next. So one on earth am I passing to the next layer?
Exactly. So what you're passing is the output of layer one. So whatever layer one is giving, you're giving it to the next layer. That's all it is, right? In an ideal scenario, what I would want is something very close to what you aim for, where the error is not calculated at one point, or in other words, the error can be somehow redistributed to the different nodes in the neural network, right? That would be an ideal situation. The good and bad side of the approach is, the bad thing is we are never going to get close to that because by definition a hidden layer doesn't have a correct answer, right? But the good news is we are going to do something very close to what we want. where we are going to calculate the error at one point and we are going to kind of redistribute that error back into the neural network at some point down the next class. Did that make it better?
No, but I will do a lot of research between now and the next class. I'll be listening very carefully.
Okay.
Okay. Don't worry. I think we are on the same page. But from what I understand is, so there is hard to calculate the exact error term, or it's even possible to calculate that during the hidden layer. But and then also and it's different across industry too, right? Maybe some industry the error might be higher, but it's still correct. It's still good. But in some other industry, the error number might be small, but it's still wrong. I wonder if that makes sense. Sorry.
That does, yes. So that is from the point of view of a domain expert. That's something that the domain expert should design. An isolated AI person cannot really make that call. Yeah.
Professor.
Yes.
In engineering,
Yes.
yeah. So when the system has an error, in engineering, we would have a feedback loop. We have a feedback loop to correct the errors. In this case, it looks like we need to send the error backwards.
Intuitively, yes, correct.
Send the error
what we would.
backwards. Into the neural network again.
Correct. That is one of the things that got Jeffrey Hinton the Nobel Prize, I think last year or the year before that. That is what's called backpropagation. And we'll come to that in a minute. That's the ideal situation. But before that, people literally used to just randomly initiate weights, do this single forward pass, calculate the error. If it's too high, do a different set of random weights, forward pass, calculate error, different set of random weights, forward pass. So they will do this iteratively for different weight combination. Now it's extremely inefficient, as you guys mentioned, correct? I mean, you don't need a PhD to say that. It's inefficient, and in many situations, you might not even come up with the correct set of numbers. Because imagine the point of neural network is I want to work with huge volumes of data, right? I want to work with hundreds of features. Now, if I have 100 different combinations, 100 different weights, the math that is involved in the weight adjustment randomly is doesn't even make sense, right? So people quickly lost interest in neural networks, and that kind of caused the second winter or the first real winter in neural network, where people said, okay, this looks good, but it's not efficient. We can't. And remember, the computation was a problem in the 80s and in the 70s. We didn't have efficient thinking of how AI could be used to predict stock movements using historical data, but programmers still need to do backtests because AI isn't capable of self-checking. Okay. I don't know in which context this is relevant, but I'll come to that. Okay. So that is really the problem with random updation of weights, right? That leads us to the next part of the lecture, where we are going to try and find if there is a systematic way to update the weight instead of doing it randomly. Okay. So instead of randomly updating weights, we are going to update the weight systematically. And for this, we want to start. I mean, we always start randomly because we have absolutely no idea which combination of numbers is going to give a correct answer. So we start randomly, and then if the output is by magic or by divine luck, if it turns out to be correct, which means that we get a small error, then we will not do anything, we will just stop the training. But if the output is too high, like if the error is too large, we want to find the direction in which the error is large, where we want to see if there's a correct answer. We get too high of an output, then we decrease the weights that are attached to the high inputs. If the output is too low, then do the reverse, increase the weights that are attached to the high output. In a normal situation, this is the systematic variation, the systematic updation plan that I would want to implement. Okay, so it's kind of like finding the area which has the least error in this multi-dimensional feature space. Okay, there is an algorithm for that. Many of you might be familiar with it. It's called the gradient descent, right? So the idea is very simple. I have my feature space, the feature space which the neural network has created. I want to find within the feature space the correct combination of weights and bias, which will give me the minimum error, right? This is my goal, right? But the feature space is so multi-dimensional that if I start randomly, if I start with random weights, I'm probably going to land up here, end up here, where the value of the minimum the point where the error is minimum is very very far away. Okay. Next time I randomly initiate, I land here. Next time I land here. So that is really very tedious. So I come up with a plan and I say, okay, now I initiate the weights randomly in this multi-valley, multi-dimensional error space. Okay, I'm standing here, right? I want to find the path which has the steepest descent, right? And I want to follow that path, right? That is the idea of gradient descent. Okay. How many of you have heard of the term gradient descent? Okay. So lots of hands going up. Nimish, great. Okay. So one of you, can you explain how we can use gradient descent to update the weights in a neural network?
It's basically finding the direction in which the error can get reduced and use that as a differential to apply over the earlier iteration weight by multiplying with the learning coefficient.
Oh, so yeah, let's come to the learning coefficient in a bit. But the idea is basically finding the. Okay, we try to explain this in a very figurative manner. In the sense, I try to, people generally, when they talk about gradient descent in neural network, they talk about this multi-dimensional error space. What I mean by that multi-dimensional error space is there is W1. If there is W1 and W2, it's x-axis and y-axis. If there is W1, W2, W3, then it is a three-dimensional space where I can locate a point using x1, y1, z1. If I have W1, W2, W3, W4, W5 up until W something, okay, and then I have a set of hidden layers. I have a hidden layer with a set of neurons. Again, there are weights for those. Now, I'm just creating more and more weights, and I'm trying to find the best combination of weight, which will actually give me the minimum error, right? So that's the analogy that we are using in neural network. We are trying to find in this multi-dimensional error space, what's the point which will give me the minimum error. In order to do that, we initiate the weights randomly, okay, and we land somewhere, okay. We try to find the slope at that point, okay. Like if I land here, I try to find the slope at that point, and I try to go in the reverse direction of that. I try to go in the direction which will take me towards the point where the error is minimum. Okay, so the gradient is a collection of all the partial derivatives of all the weights. Okay, and what I want to do here is for a small change in the weight, how will my error change? I'm going to use this approach to minimize my error, right? So given the function e with all these parameters w, I'm thinking e can be minimized by moving in a direction opposite to the gradient of the error with respect to the weight. Okay, that's basically what gradient descent is. So let's say I land up here in my first weight initialization. Okay, I find the rate of change of the error at this point. Okay, and I try to keep going in that direction until I reach the minimum. So now instead of randomly initiating weight, I am calculating the error. I'm doing some math there. I'm finding what is the rate of change of error at that point, and I'm changing the weight systematically instead of randomly. Did you get that? Did you get that approach?
Yes, I just want to clarify on this. So the parameters in here is x is like the error and y is like the weight. Oh, what? Sorry, I might miss this. I know that we try to find a relationship between the weight and the errors, but the x and y here.
So the x and y here are the axis in your weight space, in your feature space, where the error is minimum. So that's it. It could be if you are talking about a neuron over. I go back to the whiteboard. Give me a minute.
Yeah.
Okay, 1 minute. It's loading. Okay, so if you talk about this neuron, the x and y are the weights that uh, the feature space is basically made up of the weights that come to this neuron, right? For simplicity, we have used x1 and y1, which means we are only considering these two. Okay, so what correct combination of these weights will reduce the error, will reduce the overall error. Okay, when we talk about multi-dimensional feature space, we are talking about a feature space which has F1, F2, F3, F4, F5, and also H1, H2, H3, H4. Which correct combination of these numbers will give me the least error? Right? That's what we are trying to calculate in this approach. Did that answer your question?
Sir, I think if I could maybe just try to answer the question, I don't know. She responded positively. On the x-axis, that is the value of the weight, and y is the error. Correct? Or
Yeah, that's what I'm thinking too. I'm trying to
you
clarify.
had it the other way. Yeah, you had it the other way around when you first said it, but I think that's what she's saying, sir.
Yeah. Yeah, I think Y is the error rate and X is the
Yes.
weight. That's what I'm thinking too.
Is that correct, sir?
You're saying that X is, can you repeat that?
X is the you're changing X, or the weight, the value of the weight, and finding the minimum, which is minimum error, which is Y.
Correct.
Yeah. Okay.
But it is not just Xn. That's the point I'm trying to make. It's a multi-dimensional feature space where the X and Y, we are simplifying it into 2 dimensions. Right, but it is actually you can't imagine that it's a multi-dimensional space where there is one correct combination of the features which is going to give me one minimum error. Alright, so the scale is just on a multi-dimensional feature space. That's the only change that I would make. Yes.
Thank you, sir.
Okay, so that is the idea of gradient descent, right? And in gradient descent, we try to basically, so now we have got an approach which is not entirely random, right? We have a way to systematically change the weight during training or update the weight during training. We are going to initialize the weight randomly, but once that initialization happens, if we land anywhere in this huge feature space, in this error feature space of error, okay, we have a way to systematically go down and reach the local minimum. At least in theory, or the global minimum. In theory, okay. Now the gradient descent, there is one problem. There is this problem of local minima versus global minima. Let us say that I land here in the feature space. First time I make an I initialize weights. I come here, okay, and then somehow using gradient descent, I am able to update the weight, find the error, and update the weight. Right. This is my second updation, and then this is my second updation. My third, my fourth, and in my fifth weight updation, my error is actually going in the opposite direction, right? Because I'm already here. Now, the algorithm is going to think that, okay, now, in the previous iteration, I was here, the error got minimum, error got reduced, now the error is increasing. So, I'm going to stop training because I have reached the point of minimum error, right? But did you notice something? There is actually a point of minimum error which is sitting here, where this point is lower in the error space than this. Why didn't we get there? Because the training never reached there. Right? The training stopped because the direction of error flipped in this point. Right? That is the problem of what's called the local minima. So in this feature space, I can hit a point where the error could be less, but it is not as less as it can get. Right? That is a problem with gradient descent. We have ways to address this, but let us just think of the approach and see if that is the best approach that we can have. Okay. What we want is something like this, where the error actually goes to what is called the global minima. Called the global minima, where that's the point where the error is as low as it can get. A local minima is still reduced error, but it's not as low as it can get. A global minima is the minimum is the point in your multi-feature error space where the error can get as less as it can.
Professor, there is a very much a possibility that we may get trapped in a local minima, and
Yes, very much.
when we try to find the global minima, it is basically a trade-off between the exploitation versus exploration, right?
Correct. Correct.
So, if we randomly start with different initial weights, we may be exploring many such possible minimas, right? Could that be a strategy?
Correct. So that is something that people use, and that is we are going to discuss that as a solution.
Okay.
We are talking about these things historically, right? So things have evolved so much that that is actually the default position nowadays in training neural networks.
Okay.
Okay. Okay. So now we have a slightly better way of changing the weights, and we are letting the neural network actually learn. Okay. We are not feeding it anything. We are not manually giving it any features. We are letting things be a little bit on autopilot, right? And remember, that was our goal when we started with learning, right? Now, the change in weight is happening organically and kind of on its own instead of we giving specific inputs, right? So instead of the first approach of randomly initiating doing forward propagation, we have a way of updating the weights in a systematic way, in a systematic manner. It is still forward propagation, right? So we are still starting random. We are getting the output. If the output gives small error, we don't do anything, we just freeze it. If the output is too high, we have a way to reduce the weight according to the direction of the error, right? If the output is too low, then we increase the weight. Now here, WT is my old weight. WT plus 1 is my next, is the weight in my next iteration, right? So I'm doing a okay. So I'm doing a dou v by dou w where I'm finding the rate of change of the error when I change the weight. Okay. And I'm changing the error term and I'm changing the weight systematically. Now there is this one small term called alpha sitting here, which we did not talk about. Okay. So the alpha is basically my what is called the learning rate. So the alpha is the learning rate, which basically determines what is my step size while I walk through the gradient descent. If I go back to my previous step, I can reach from this point, I can reach from this point to this point in 1, 2, 3, 4, 5, 6, 7 steps, or I can take 20 steps, right? That is another hyperparameter that I can actually control, right? And that is what is called the learning rate, which basically determines what is my step size between two iterations, between two weight updations. Okay. Am I going to update my weight by a big amount or a small amount? Again, that is an optimization where if I'm going to update my weight if I'm going to update my weight in a large amount, I might actually miss the minima and I might actually go to the, in one iteration I'm here and in the next iteration I'm here. I completely missed the minimum value, right? If I take a very small learning rate, then lot of computation is required, lot of resources are required, time is required because in order to reach from this point to this point, I'm going to take 20 iterations, right? So that is another hyperparameter that I can control, which is the learning rate, the step size in which my weights are going to be updated. Okay.
And so this learning rate is also automatically calculated during the learning process.
No, we
right?
fix the learning rate.
We fix the learning.
Yeah, it is a hyperparameter where when we start the training, we say, okay, learning rate should be 0.5 or 0.1 or 1.5, something. We give a number and then they say, every time you update the weight by this much.
Got it. So it's the increment that we would like to add, but we will assign according to our experience. Like and also the learning rate is different across industry. That's what I'm thinking too.
Correct.
And it might be also according to the resource limited. Maybe because each learning rate will cost a lot, that it will determine our learning rates that we'll give it. Like what's the limitation like that we give to that's what I'm thinking. I mean that's what I'm understanding because learning rate we will give it will according to the resource that we might have or limitations that we might have.
Yeah. So for the matter of any hyperparameter is a matter of experience, right? So how many neurons you want to put in, how many layers you want to put in, what's going to be the learning rate, what's going to be the cost function. So a lot of this is actually experience. So depending on how big the data is, you kind of intuitively come up with a number. And when the training is happening, if you see that the update is happening too slowly, you just stop the training midway and you update some of these parameters and start the training again. So yeah, so that's usually how people do it. Yeah, you can monitor the progress, and if you think it's going too slow, just stop, give few numbers, and restart it.
Got it. And may I ask just for clarification purpose, is the learning rate between 0 and 1 again? Or it can be, it can be like 1x, 2x, 3x, right?
Yeah, so it's usually a number that goes from 0 to 1. I mean, we'll do this when we do the lab part. We'll actually play with these parameters and build something.
Thank you.
All right. Okay. Now, what is
So would the learning rate, if it's higher, will it increase your computational power?
It will not increase it will increase the demand for the computation. If the learning rate is too low, if it's too small, right? Because it would need more iterations to reach a point.
Got it.
Now, Professor, I have a question on this. Now, if the learning rate is too small, then the progress might get submerged in the normal variation, right?
I didn't quite get that, but
now,
go ahead.
What I'm saying, like when I'm having the same weight itself, And when I go for multiple iterations, I am not learning, and I stop learning, and I'm using the same weight. But then, based on the data, what is being processed, or based upon how I am doing the split, there will be always variations. Accuracy would differ, the precision recall, everything would differ based upon the way the data is split or based upon the data what I'm using for inference. Now, that is the variation which I'm calling as the natural variation, which is not due to the weights, but it happens because of the randomness. Now, if I am keeping the weight, learning rate very small, then it may misguide as though like I am getting an improvement or I have to go back off or something, but it may be truly random, right?
Yeah, so there is some amount of there's actually a lot of credibility in your argument. But when you actually do the training, if the learning rate is small and the network is still learning, the change in accuracy will always be in one direction. Like it will keep on improving, however small it is. Right? So 87.5, 87.52, 87.51, 87.53, 87.53, 87.52. So you see, there is always an overall increase in the trend. Whereas if it is random, even if the learning rate is too small, it will fluctuate up and down. 85.3, 88.2, 84.9, 84.3, like that.
Professor, I have seen sometimes it doesn't, the error doesn't decrease monotonously. It has a kind of a sawtooth kind of a corrugated performance. That's why we use patience, right?
Correct.
So
Yes.
I'm saying when we have, for example, a patience of 5 iterations, right? And now, like whether the learning factor, the unit size will go to the lowest level that it gets submerged within this.
Yeah. So that's why I said that there's a lot of credibility in your argument. So there's a lot of credibility, but even with the sawtooth approach, you will find however small it is, if the network is still learning, you will find a trend in the direction.
Got it. Got it. And we are limited ultimately by choosing the right patience value.
Yeah. I mean, even before you get here, if your learning rate is too small to come to 87.5, you could have started with 20.1 and then 20.3, 20.5, 20.7, 20.5, 20.8, 20.6, like that, right? So remember the number of iterations that have gone into the system in order to reach 87. Right? So no amount of patience, like literal patience, human patience, people can have. So they just stop the training right there, and they actually adjust the parameters and start the retraining. That is usually what happens.
So our adaptive learning rate, right?
Adaptive. Yeah.
Thanks, Bruce.
Okay. Okay, so I think I'll start back propagation next week because that's the next big topic. But I'll start with the problem. Okay. Now let us say that using gradient descent, I will show the whiteboard in a minute. Okay, let's say that I'm using gradient descent. Okay, let's say I'm using gradient descent. in order to update my weight. Okay, and somehow I have updated. I found a weight which gives me less error. So I have fixed W1 as that weight. Now, what is the guarantee that when I start doing W2, okay, the error will still be the same direction where I want it to be? Or in other words, ultimately, the error is going to be a combination of all these weights. Okay? But what I'm doing, I'm not updating all the weights at once. I'm getting one error score, which is actually a combination of all the errors, but I'm updating only one weight at a time, right? So an optimal weight value for W1 will probably immediately collapse once I start updating my W2. Okay, so it's like I have 10 different knobs and I'm adjusting only one knob where I'm getting some value, right? But what I actually need is a combination of knobs, right? And there is no guarantee that once I start playing with knob number two, knob number one will actually behave the same way that it behaved before, right? So gradient descent is a great technique, but there is still the problem of only the forward pass where I can update only one weight at a time. I'm not updating a combination of weights. Okay, that created kind of another winter in my overall neural network world, right? So the first time people just thought, okay, this is not going to work because we have just reinvented the wheel, logistic regression. The next time is, and then people solve that by adding more neurons, by adding, by coming up with the gradient descent approach to upgrade the weight and all that. But still, people quickly lost interest because it is taking a lot of computation and a lot of resources without any guarantee of result, right? So that kind of started another age of winter until this technique called back propagation was implemented. And that's where we will start our next session. Any questions still here?
Sir, do you call that interaction between changing the, say, two weights interference?
It should interfere, right? Yeah, because we need a combination of weights that works best.
But because of the interference, we just want one weight at a time, and then find what that output is.
Yeah, because we can work only with one weight at a time.
Okay. Thank you.
So doctor, the GD is good, but it's exhausting the system. This is what I understand.
Correct.
Or
So the
consuming
gradient descent is good, but it's exhaustive. Correct.
Okay. Thank you.
Sir, even if we fix one weight at a time, okay, isn't that a move in the direction of reduction of error? So why did the winter happen?
Of course, it's definitely better than. Yeah. So it's definitely better than the random initialization of weights. But remember, the power of neural network or the claimed power of neural network is you can deal with hundreds of features, right? So when we have that sort of a combination, updating a combination of weights in that scale becomes difficult. And then you end up saying, okay, this works only if the number of features is 10. So I don't even need a neural network, right? I can go back to my ML. ML can perform far better.
Got it, sir.
Okay. So if there are no more questions, I think we can end the session and meet next Saturday again.
Thank you, boss.
Thank
Thank
you.
you.
Thank you.
Thank you so much.
Thank you.
Have a good
Thank you,
night.
sir.
Have a good rest of the day. Thank you. Thank you.
Good night.
Good night. Have a good night. Have a good day, everyone. Thank you.